have you ever really stopped to think about that black stuff we put in our cars? I mean, what is it actually? Its journey is just incredible. It starts with microscopic life millions of years ago and ends up in, well, literally everything around us. So let's trace that amazing path, from plankton all the way to plastic.
Let's just start with a number. 97 million. That's how many barrels of crude oil the world gets through every single day. It's a number that's almost impossible to wrap your head around, right? It's the energy that powers our cars, our planes, our entire way of life. It really is the lifeblood of the modern world.
But again, what is this stuff? How on earth do we take this thick, raw liquid that's buried miles underground and turn it into the gasoline in our tanks or the plastic in our phones? That's exactly the journey we're going to break down right now.
To really understand petroleum, we have to become geologists for a minute. We've got to go back in time, and I mean way, way back. Let's dig into the ancient, multi-million-year-old recipe for making oil.
Okay, first things first, let's bust a huge myth. Oil does not come from dinosaurs. I know, that's what we all thought as kids. The real source is actually much, much smaller. The whole story begins in ancient oceans, with trillions and trillions of tiny little marine organisms.
You know, the name itself actually gives us a massive clue. Petroleum. It comes from two Latin words, petra, meaning rock, and oleum, meaning oil. So it's literally rock oil. And that name perfectly describes where it comes from.
So think of this whole process like geology's ultimate slow cooker. Over millions of years, all that dead plankton sinks and gets buried under layers of sediment. At first, some gentle heat and pressure turn it into this waxy stuff called kerogen. But as it gets buried deeper and deeper, the intense heat and pressure, a process called katagenesis, it cracks that kerogen into the crude oil and natural gas we use today.
So, okay, the Earth has cooked up all this oil. But it's not just sitting in giant underground lakes waiting for us. Nope, finding it is more like a high-tech, subterranean treasure hunt for some very specific geological formations.
It all starts with what's called the source rock. This is that organic rich layer where all the plankton got buried and cooked. You can think of this as the geological kitchen, where the whole recipe gets started.
Now, once it's formed, that oil is lighter than the water trapped in the rock around it, so it naturally starts to move upwards. It's looking for a new home, and that home is called a reservoir rock, a porous layer like sandstone that can hold the oil just like a sponge holds water.
But a sponge can leak, right? So the final, absolutely crucial piece of the puzzle is the seal rock. This is a layer of rock that oil can't pass through, like shale. It acts like a lid, trapping the oil underneath it. So you need all three, the source, the reservoir, and the seal, to create a trap. That's your subterranean treasure chest.
So how in the world do geologists find these hidden traps? Well, this is where some really cool tech comes in. They use things like magnetic and gravity surveys to get a big picture view, but the real star of the show is seismic prospecting. They literally send powerful sound waves deep into the earth and then listen to the echoes that bounce back. It's like giving the planet an ultrasound to create a super detailed 3D map of what's hiding miles below our feet.
Okay, mission accomplished. We found the oil. But now comes the really tough part, actually getting it out of the ground and then cleaning it up so it's ready for the next step. And the main tool for that job is the rotary drill. Just picture this massive rig spinning a powerful drill bit at the end of a super long string of pipe. It grinds its way through miles of solid rock to finally punch into that reservoir and tap into the high-pressure oil and gas inside.
Now, the stuff that comes out of the ground, well, it's messy. It's not just pure oil. It's full of this really corrosive, salty water. So the very first thing they have to do is clean it. They mix it with fresh water, heat it up, and then, and this is the cool part, they zap it with a high-voltage electric field. This forces all the tiny water droplets to clump together and sink to the bottom, taking almost all the salt with them.
All right, our crude oil is clean. Now it's off to the refinery. And the heart and soul of every refinery is this incredible piece of engineering that's designed to do just one thing: separate the thousands of different types of molecules that are all mixed together in crude oil.
I love this analogy. You should think of the atmospheric distillation tower as a skyscraper, but for molecules. Hot, vaporized crude oil is pumped into the bottom. As the vapors rise up this massive tower, they cool down and condense at different levels, basically sorting themselves automatically by size and weight. So let's take a quick walk up this skyscraper. All the way at the cool top, the lightest, tiniest molecules, like propane gas, are collected.
A little further down, where it's a bit warmer, we get naphtha. That's the key ingredient for gasoline. Below that, kerosene for jet fuel condenses. Lower still, we get diesel. And then, at the very bottom, where it's still scorching hot, all that's left is the heaviest, thickest, gooeyest stuff called residue.
But here's the thing. This whole distillation process, as clever as it is, creates a big problem for a refinery. See, it gives you a fixed amount of each product. And the world demands way more of the light stuff, like gasoline, than it does the heavy stuff.
So you end up with way too much of these long, heavy, low-value molecules from the bottom of the tower, and not nearly enough of the short, light, high-value molecules that we all need for gasoline. So, what do you do? How do you solve that puzzle?
The solution is an amazing process called catalytic cracking. You can basically think of it as a molecular hammer. Refineries use a combination of intense heat, high pressure, and a special substance called a catalyst to literally smash those long, heavy, not-so-useful molecules into smaller, much more valuable ones. It's how they turn cheap residue into premium gasoline.
So after all of that, the finding, the drilling, the cleaning, the separating, and the cracking, what do we actually get? Let's bring this whole incredible journey home and connect it back to the products we all use every single day.
So let's look at one single 42-gallon barrel of crude oil. What does it become? Well, get this, nearly half of it, about 45%, becomes gasoline. Another 20% or so becomes diesel. So right away you see that transportation fuels just completely dominate. It shows you how central petroleum is to just moving ourselves around the planet.
But, and this is the part that blows my mind, it is so much more than just fuel. See that little slice for petrochemical feedstocks? That is the starting point for a mind-boggling list of things. The plastics in your phone and water bottle, the polyester and nylon fibers in your clothes, detergents, the asphalt on our roads, even critical components for life-saving medicines. It is woven into the very fabric of our modern lives.
So there you have it. From microscopic plankton dying in an ancient sea, through millions of years of being pressure-cooked by the earth, to this global high-tech system of exploration, extraction, and refining, that is the unbelievable story of petroleum. It's the substance that has built our modern world, which of course leaves us with one heck of a question to think about. What's going to power the next one?